Very good morning, students. Welcome to IIT NEET Foundation or Focus C program by Krishnaveni Talent Schools and the Mastermind Schools. So once again, I welcome all the participant branches so far for today's session. As you can see on the screen, and you are well aware, my subject is physics. We are in class 7. Today we are going to start a new chapter, the chapter number 7, circular motion. Right? This is a 7th chapter. So far we completed 6 chapters. Today we are going to start a 7th chapter, circular motion. And today is the session number 1. But before going to start a new chapter, let us remind you that the syllabus for test 6, test number 6 is on 30th December. So syllabus is the 6th chapter, that is work, power, energy, which already completed in the last class, right? Work, energy and power. This is the syllabus for the coming test 6 exam, that is, which is on 30th December, Monday, right? So prepare well. You already completed a complete conceptual explanation. You go through the material and complete all the worksheets related to work, power, energy. Whereas today we are starting the new chapter, that is, which is for test 7 syllabus. This is, which is to be in the last Monday of the January. So before knowing about the circular motion, we have to recall what is motion actually, because we already learned in the first chapter what is motion, right? So all of you know that motion is nothing but change in the position of a body from time to time, right? If a body changes the position from time to time, it is said to be in motion. Time to time change in position of the body or change in position of the body with respect to time is called motion. Means a body is said to be in motion if it changes its position from time to time, right? That is called motion, already we discussed. There are various types of motions we'll see in our day-to-day life, right? Various types are there. It may be, for example, it may be linear motion, right? Linear motion, again 2 types. If the body moves in straight line, that is called rectilinear motion. If the body moves in curved path, that is called curvilinear motion, right? So your body is going in straight line, that is called rectilinear motion. If the body moving along the curved path, it's taking turn like cars and all, that is called curvilinear motion. So like that, there are oscillatory motion, vibratory motion, random motion, many types of motions we discussed. Out of all, there is one special type of motion called circular motion. You all know what is circle, right? In mathematics point of view. So this is a circle. Circular motion. So motion of the body along a circle about a fixed point. This is a fixed point. And around the radius. Suppose when you go to the circus or exhibition, when you go to circus or exhibition, you can find giant wheel. Most of you know what is giant wheel. Keep rotating around the same axis continuously by about the fixed point. So suppose Earth, our Earth is revolving around the circle path around the sun from last so many million years. Similarly, electrons moving around the nucleus in a curved path, which is called circular motion. Your cycle tire or your vehicle tires, all the tires will follow the circular path. So many examples in our applications, day-to-day life, where circular motion comes into play. So this chapter will discuss about the what is circular motion, where we can find this type of motion in our day-to-day life, and how the terminology is different from linear motion and circular motion. Okay, so our today topic is circular motion, session number 1. So as once again I remind you, circular motion is one type of motion, is one kind of motion where body follows a circular path with constant speed. Speed is constant but changing the direction. If the direction changes, then only it follows the circular, right? See, every point there is a change of direction. So moving at a constant speed. See, Earth is revolving around the sun with same speed. That is the reason where the day and nights, days, years, same way. It's not changing the speed, or it's not coming slow down. It is moving at constant speed. Such motions which follows the curved or circular path with constant speed are called circular motions. So you can see so many examples of this circular motion. Okay. So motion, you know, everybody already we discussed in the first chapter. There are so many types of motions are there. Out of that, circular motion is the special case. Special case of motion is called circular motion, right? Okay. When you move next slide, we'll start our real chapter. So circular motion, chapter number 7. So what we learn here, we learn about the terms related to circular motion. When a body moving in a circular motion, we'll come across some important terms. Like when a body is in motion also, we'll come across velocity, displacement, right? Acceleration. Many things we can come across. Same way, we can come across some new terms when the body moving a circular motion. Okay. Then the second part is we'll discuss about the centripetal and centrifugal forces, which are responsible for body to move in a circular path. If these forces are not there, body cannot follow the circular path. It may go straight line. So one body is moving a circular path without falling into the center. So why Earth is moving around how Earth is moving around the sun? How electrons moving around the sun is because of centripetal force. Then why Earth is not falling into sun? Is because of the centrifugal force. So we'll discuss about these two forces in details in coming classes. But first, we'll start with what is circular motion, right? So just let me explain, then we'll go for one video also. So the motion of an object along circular path. A motion of an object, you can note down the first synopsis number 1. Very important point. Note down first point, the motion. The motion of an object along a circular path is called circular motion. Please note down, all of you. Means, see here, a body is following a circular path. See direction, you can see it is coming like this. If it goes straight, we can call linear motion. Suppose body started here, A, move up to here, B. This is the straight linear motion, straight line motion. But a body following the path like this, circular path, then it is called circular motion. Right? So how it is following circular path, that will come across. But you know this point. The motion of an object along a circular path is called circular motion. Right? So you can draw this diagram also with arrows. See arrow how it is going. This is the center. It is a fixed point. This is the radius we can call, or this is called diameter, whatever it may be. Okay, along the circular path, body is moving. So it is called circular motion. So hope all of you clear about circular motion. The motion of an object along a circular path. Now, the point number 2, the uniform circular motion can be two types. It may be uniform circular motion or non-uniform circular motion. Already we have seen what is the uniform motion. If body covers same distance in same time, means it is moving the constant speed. Same distance, it's same time, then you can call it as a uniform circular motion. Uniform motion. So reciprocal, it is covering the different timings, different distance. Already given so many examples when you are discussing about the motion. Okay, see here. The point number 2. When a body moves along a circular path with constant uniform speed, or constant or uniform, constant speed, its motion is called uniform circular motion. Note down the second point. Note down the second point as, so this one. You start from here. When a body moves along a circular path with a constant speed, constant or uniform speed, its motion is called uniform circular motion. What is called? Uniform circular motion. Right? The point number 2. So we'll discuss about some examples of uniform circular motion. Then we'll go to next part. See, examples of uniform. Point number 3, you can write examples of uniform circular motion. Number 1, you can see motion of planet around the sun. Not only Earth, all the planets revolves around the sun with uniform circular motion. That is the constant speed. Second example, motion of satellites around the planet. Suppose when you are launching a satellite into the Earth orbit, they move constant speed and gives out lot of information for us. They gives out lot of information. Okay, the third one, the tip of the second hand's watch. You see the watch, second hand will be there. Hour's hand, minute's hand, second's hand. Second hand will always move. So that also moves with there. That is the reason we get the same constant timings exactly without changing. So the tip of the second hand's watch exhibits uniform circular motion, right? Then fourth, a stone tied to a string. You take one stone tied to a string or rope or thread, then rotate. That is called whirling. Whirling of stone also follows the circular motion. So please note down all these 4 points. Point number 3, examples of uniform circular motion. 1, 2, 3, 4. Right? 4 points for the uniform circular motion. Examples. So first you wrote what is motion. Then you wrote what is circular motion. Then you wrote what is uniform circular motion. Then examples. 4 examples of uniform circular motion. You complete that. In meantime, I'll show you one video also after completing writing. Right? First point is definition of circular motion. Second point is definition of uniform circular motion. Third point, it contains again 4 important examples. Examples of uniform circular motion. Written all of you. Okay. So the motion of an object along a circular path is called circular motion. The first point. Second point, when a body moves along a circular path with constant speed, constant or uniform speed, is known as uniform circular motion. Example 1, motion of the planets around the sun. Maybe you can remind, if you close your eyes, you can see all circular motions observed in day-to-day life. Second one, motion of satellites around the planets. Third one, a tip of seconds hand of watch. And fourth one, a stone tied to a string and rotate. Right? It is also, that is whirling of stone, you can call it as whirling, means rotating. When you rotate stone like this, follows the circular motion. You might have seen in the circus, a person moves with a bike around the globe. Around the globe, they'll move with the bike. That is also comes under circular motion. Like so many examples you can see about the circular motion. Right? Now, before going for the next, let me show you a video on the circular motion, and if possible, even with the uniform circular motion also. Right? Watch carefully.
What if I'm moving in a circle on this ride at a constant speed? How am I accelerating? Anytime an object is traveling in a circular path, it is accelerating because its direction is constantly changing. Now remember, velocity is a vector. It has magnitude and direction. If either changes, velocity changes. And acceleration is defined as a change in velocity. Let me show you an example.
Yeah, see, that's very interesting. You can do this.
Ever wonder why you can swing a bucket of water like this?
Bucket of water.
And the water doesn't spill out? It's because of centripetal force. It's a word that means center seeking, and it's written F sub C.
We'll learn about that.
Centripetal force is any force that makes an object move in a circle. There's more than one kind of centripetal force: friction, tension, the normal force, or gravity. And any of these can act as centripetal forces if they cause the object to move in a circle. Here's another way to say it. Centripetal force is the net force acting on objects that keep them moving in a circle. When I swing the bucket, there are two questions. Which force makes the bucket move in a circle, and what keeps the water in the bucket? It's a fine balance here in keeping the water in the bucket. So what forces are acting on the water in the bucket? Well, let's draw a free body diagram of the bucket first when it's at the top of the swing.
How water is?
The force of gravity, F sub G, acts down. Tension, F sub T, acts down on the bucket as well. The force of gravity will act down regardless, but the tension force will always act toward the center of the circle. In this example, the tension force and the force of gravity create the net force, and together, they make the bucket seek the center of the circle through the centripetal force. In a free body diagram, you don't write centripetal force per se. You write in the specific force or forces causing the centripetal motion. In this case, gravity and tension. So what forces make up the centripetal force when the bucket is at the bottom of the loop? You can see that the tension force still acts towards the center, and gravity continues to act down toward the earth. So what keeps the water in the bucket? It's the normal force of the bucket on the water's inertia. Tension keeps the bucket moving in a circle. The water within the bucket experiences the normal force from the bottom. This force keeps the water moving in a circle. If we were in the middle of space and there was no gravity, the water would still stay in the bucket as it was swinging in a circle, thanks to the normal force. And what force keeps the bucket going in a circle? Well, that's easy. It's the tension of the rope.
Observation again.
Okay. What if there's no rope? For example, what force keeps a satellite orbiting the Earth? It's gravity that pulls the satellite toward Earth and keeps it in orbit. So the centripetal force is Earth's gravity. It's the tether that keeps the satellite orbiting around a central point instead of flying off into space. But keep in mind, it has to be going at a certain velocity to stay in orbit. If the satellite slows, it will give way to Earth's gravity and fall to Earth. So let's take a few circles around this track. The only difference between this and the bucket of water swinging in circles, the bucket of water swings in vertical circles. The circle we're traveling in here is horizontal. But the good news is the same principles apply.
You know, it might be right.
So based on that, what forces keep this cart moving around the circular track? Frictional force is at work helping the tires grip the track and keeping the cart in a circular path. Vertical forces on the cart cancel out. The cart is center-seeking, only in the horizontal direction. And how about when you make a sharp right turn and your body is slammed up against the left side of the car? What causes that? Is it centrifugal force? Absolutely not. Turns out centrifugal force is not a force at all. The real reason is explained by Newton's first law. Just like the water in the bucket, your body wants to stay in the same motion, except the go-kart is turning to the right. Your body is resisting the change of the circular motion and wants to continue in a straight line. That's inertia. So the force you feel is the car running into you as it seeks the center of the circular path in which it is traveling. Okay, so let's go back to our rotating bucket of water. We know why the water stays in the bucket. It's experiencing uniform circular motion. That's when an object moves in a circular path at a constant speed. Now, what do you think will happen to the bucket if I were to let go of the rope? What direction will the bucket move? The bucket's velocity is called tangential velocity, V sub capital T, because if tension lets up at any given moment, the object flies in a straight line that's tangent to the circle. So the direction of tangential velocity changes constantly as the object travels in a circular path. To measure how long it takes for the object to go in a full circle, that's called its period of revolution, capital T, or simply the period measured in seconds. Let's go to another ride. Recall from another segment that velocity is a vector quantity. It has direction and magnitude. The magnitude of v is speed, which is constant for uniform circular motion, but we will call it our tangential velocity, since this speed and the tangential velocity magnitude have the same value. This ride does one full circle. The distance traveled is called the circumference and is calculated by multiplying the radius by 2 pi. And the time it takes to make a full circle is called the period. You write that as capital T. The tangential velocity of an object traveling in a circle is the distance around the circumference divided by the time it takes to travel around the circle once, which is the period T. And remember, if an object is moving in uniform circular motion, it is accelerating because its direction is constantly changing. This is called centripetal acceleration. Centripetal acceleration is equal to the tangential velocity squared divided by the radius of the circle that the object traces out. Centripetal acceleration is always perpendicular to the tangential velocity and always acts in the same direction as the centripetal force that's causing the object to move in a circle toward the center. Think of Newton's second law. An object will accelerate in the direction of the net force acting on it. In this case, the sum of the centripetal forces is equal to the mass of the object moving in a circle times the centripetal acceleration.
F is equal to ma.
Okay, here's an example. Imagine you're riding a roller coaster through the bottom of a circular loop. The loop's radius is 15 meters, and your tangential velocity at the bottom is 11 meters per second. If your mass is 50 kilograms, what is the normal force exerted on you? Drawing a free body diagram, we see that the two forces acting on you at that moment are gravity, down, and the normal force, up. By Newton's second law, we can write that the normal force minus gravity equals your mass times centripetal acceleration. Since centripetal acceleration equals tangential velocity squared divided by the radius, then you can substitute that to the right side of the equation. And to find out the normal force, rearrange the equation. And since the force of gravity is mass times acceleration due to gravity, you can substitute m times g for F sub gravity. Now plug in the numbers, and we find that the normal force at that point is 893 newtons. Compare that with the normal force you typically feel standing on the ground. 50 kilograms times g, you get 490 newtons. No wonder you feel so heavy at the bottom of the coaster loop. That's it for this segment of physics. Okay,
Clearly
so let's
explain about the circular motion with a simple way. So one more is there about uniform circular motion. We can see before going.
And against a wall, and then they spin you around like a wet salad. If you've had that uniquely nauseating experience, then you know that the simple act of spinning in a circle can be intense. It also happens to be one of the most misunderstood concepts in Newtonian physics. It's known as uniform circular motion, and it's what occurs when anything moves along a circular path in a consistent way. Most of the confusion about this idea has to do with the fact that things accelerate inward as they move in a circle, a kind of acceleration known as centripetal acceleration. But you'll often hear people talking about centrifugal acceleration, pushing things outwards as they move in a circle. That's actually where centrifuges get their name. And centrifugal acceleration isn't wrong exactly, it's just not real. So to explain how things really accelerate when they move in circles, let's talk about the physics of that ride as it spins you around, assuming you're willing to step inside. I'm getting dizzy just thinking about it. In 1960, NASA was getting ready to send people to space. They knew that a big part of spaceflight would involve acceleration, so they wanted to test how much acceleration people could handle before they'd black out. Because that's what happens when too much blood is forced away from your brain for too long. So engineers tested potential astronauts by putting them in a human centrifuge, basically a superpowered version of those rides at the fair. They found that most people could withstand an acceleration of around 98 meters per second squared for 10 minutes. That's about 10 times the acceleration caused by gravity that you'd feel just by jumping in the air. With that in mind, let's say we've been asked to calculate the safety of one of those carnival rides, which means we'll need to figure out how much acceleration riders would experience.
Here there is a deep explanation is there. We'll see in the next class. So before that, so the first video clearly explains us what is exactly the circular motion by simple example of rotating a bucket full of water. When you hold the bucket full of water, half of the water, and keep rotating with your hand, no single spill of water will come down, fall down, because of the various forces acting on it. Right? Similarly, I told when a person moves around the globe by the bike also, when he reaches the topmost point, his head is down, but still he won't fall down because of some force acting on that. That we'll discuss. All these comes under the circular motion. You have seen the roller coaster, or you have seen the giant wheel. Giant wheel may be either vertically rotating or horizontally. So this all simply explains that a circular motion is a motion where the object follows circular path and with a constant speed. Speed is constant, but acceleration, body will accelerate. Because of acceleration only, it is taking the turn. As it is changing the direction, change of direction is possible, it is accelerates. Otherwise, it will go straight only. Right? Such motion is circular motion. In the circular motion, if the speed is constant or uniform, it is called uniform circular motion, where we have seen so many examples now. It may be Earth is revolving around the sun, planets may be revolving around the, satellites may be revolving around the planets, or moon is revolves around the Earth. That is also example. Okay. And seconds hand. Okay. And a stone tied to a string and whirled. When you are whirling the stone tied with a string, also an example of uniform circular motion. Right. So some more information is given here, you can see, before going for the next slide. So when a body moves in a circular path, see the last passage. So here, see, when a body moves in a circular path, its direction of motion changes continuously. You see, circular path means should change the direction, right? So even when the body moves at constant speed, its velocity is not constant because direction is changing. Direction links to velocity, speed not having any direction. Okay. Thus, the velocity of the body moving in a circular path at constant speed changes continuously. The change in velocity gives rise to acceleration. What told in that? So, when a body moves around the circular path with constant speed, but it passes the velocity due to change in the direction. As the velocity changes during change in direction, it passes the acceleration. Therefore, uniform circular motion is accelerated motion, even when the speed is constant. So, uniform circular motion, what is the constant? Only speed is constant. Velocity changes. Because of that only direction is changing. And it passes the acceleration. That's what is also called accelerated motion. So uniform circular motion is also called as accelerated motion. Okay. So before conclusion, one more point you can see. Speed remains constant. In other words, the motion of the body moving in a circular path with constant speed is acceleration motion. So uniform circular motion is also called accelerated uniform circular motion is also known as or accelerated motion. Very important. Why it's called accelerated motion? Because even though its speed is constant, its velocity changes time to time and direction changes. As the velocity changes, automatically it is a accelerated motion. You can see here. It's supposed should go like this. Body B, body A should go south direction. But because of some force, it is turned here. So it is turning. You see, everywhere there is a change in the direction. Because of direction is changing, it is following a circular path. So direction changing means velocity will be there, changes. When velocity changes, automatically acceleration changes. That's why uniform circular motion is also called as accelerated motion. Remember, right? Clear? So today we learn about the only three important things. First one is what is circular motion? A motion of a body along the circular path is called circular motion. Second one is uniform circular motion. Right. So with examples, 4 examples, that is a body moving in a circle constant speed in a circular path is called uniform circular motion. Various examples we have seen. Right. Third one is accelerated motion. So uniform circular motion is also called acceleration because body is accelerating during change of its direction. Okay, these are the very important information about the circular motion, which is the part of motion. You know motion anyway. But the name circle is given because we follow in the circular path. Okay, so in next class what we'll do is we'll discuss about the various terms. How I told, in case of motion, we'll come across terms like distance, displacement, acceleration, retardation, like speed, velocity. Like this, even in circular motion also, the terms may slightly changes. Displacement is called angular displacement. Velocity is called angular velocity. Acceleration is called angular acceleration because there is an angle will come. Angle will come into play whenever there is a body moves in a circular path. Right? So many terms are there to discuss, which we'll discuss in the next class. Right? Very interesting. What is angular velocity? What is the time period? What is angular acceleration? Right? All these. Then we'll come across the 2 kinds of forces which are responsible for body to follow a circular path. Centripetal and centrifugal. Okay? Very interesting chapter this is. We'll complete by 1 or 2 classes, which is the syllabus for the weekend 7. See, there are beautiful examples for the. You can see how the giant wheel, how the revolution taking place, how the rotation taking place. All these are the example for the circular motion. It may be horizontal, vertical, or around itself, spinning around itself. All comes under the same type of motion called circular motion. Okay. Now, it's the time for the homework. Define circular motion. Give examples. Any example you can write. Even you can prepare a chart also on only circular motions and collect the wonderful pictures of examples of circular motion. Paste it aside. Name them. You can do like an activity also. Okay. So write the homework and what synopsis you wrote 3 or 4. You can mention the definition and examples of circular motion and take the signature from your teachers and parents, right? So once again, I'm demanding the syllabus for the test 6 is the 6th unit, work, power, energy. Total chapter, which is on 30th December. Okay, so that's all for today. Thank you, students. Have a wonderful day. Thank you.